Yeah, so thank you very much, John, for the very nice introduction, and I would also like to thank you very much for your invitation. I mean, it's certainly a great pleasure for me and honor to give a talk here. Now, I think we all know how tremendously successful deep neural networks are in public life and also in the sciences, but we also know that there's not a sufficient amount of theoretical foundation to really fully explain why these methods work that well. And one important direction which needs to be explored is generalization. So the question is, we train our neural network on training data. Why does it perform that well also on test data? And in this talk, I would like to look at a very specific aspect of this. And I would like to show you what we obtained in this direction. Now, then you can ask, well, I mean, if you have full control over the training process and the training data of your neural network, then it is interesting to look at generalization of those aspects. But typically, what will also happen these days and in the future is you have already a trained neural network. It is there. You don't know how it was trained. You don't know what the training data is. And so this leads us then to the area of interpretability, which asks the question, I have a trained neural network. How does it reach decisions? What are interesting and important input features to reach a certain decision? And so in this aspect, what I would like to discuss with you there is an approach we pursued where I think you have the chance to have a theoretical foundation now also for this area. Good. So I think these are a couple of examples where I think deep neural networks have a tremendous impact. I mean, everybody knows about self-driving cars, surveillance tasks, also legal issues. So job applications are sometimes now already pre-screened by neural networks or in general methods of artificial intelligence. And then certainly the whole healthcare sector, where neural networks are used to reach critical decisions, but also for imaging sciences, for instance, for magnetic resonance imaging. Now, if we then come, let's say, to the sciences, and in particular mathematical sciences, which is also my background, also there neural networks have a tremendous impact. And that's also how I came about 4 years ago to deep learning and neural networks. So there's this area of inverse problems, which asks the question, you have an operator, and you would like to invert it. Yeah, so the operator could be like a CT scan, it could be like a magnetic resonance imaging scanner, and then you would like to invert it. And there's now a long list. I mean, these are just a couple of samples of contributions, a long list of contributions which use neural networks, and the results are typically amazing, often beating the state of the art already. Then, in this area, there's also the question of partial differential equations. How do you solve them? And this area was a bit slower to embrace these new approaches, these new learning approaches. Why? Well, because there you have a very precise model, namely this partial differential equation. And then the question is, why do you need neural networks for that? But what turned out there is that in the high-dimensional regime, deep neural networks have a tremendous impact, and they are able often to beat what's called the cross of dimensionality. And last but not least, also people are now aiming to use machine learning, deep learning methods to replace mathematical modeling. And so this is in a way how I came to this area, through the area of inverse problems and imaging sciences. And before I now delve into the theory of deep neural networks, I would like to just very briefly show you what impact actually neural networks have on that area. Just show you very quickly one example we also worked on. This is the example of limited angle tomography. So what is tomography? Computed tomography. You see the image here. Well, I hope the resolution is good enough. So you have a human body, and what you compute are line integrals through it. And this gives you one slice of the sinogram. And then you rotate the device. Now, so you take these line integrals now from each angle. This creates then the sinogram, and the task is, from the sinogram, to recover the inside of the body. This is already not that easy, but it becomes really hard if we only have access to a certain part of the angle and not 180 degrees. So that's, for instance, the case in electron tomography. And that creates the problem that now you have the sinogram only in one part, and you have a huge chunk of missing data. And to recover from this is basically impossible with model-based methods, because you cannot really accurately model the interior of a body. And so there deep learning now comes into play. And what we did there, and if you like to see more details, I can talk about this also maybe later on, but so from a high-level viewpoint, what we pursue, and what I think in general in all this area a very valuable strategy is to not throw everything away what people have done before, to not throw the physics out of the window, but to use these model-based methods as far as we can. So what we do here, if you're familiar with this, we use so-called sparse regularization with shieldeds. And then we get a reconstruction which is not that perfect, and then we decompose it in a certain way to see which part is not perfect, and there we use a neural network. So in a very precise surgical manner. And then we combine both. And what you see, and let me show you the numerical results, is that this works better, also much better than if you just use a neural network. So this is the original image. We have here a 60-degree missing angle, so a huge chunk of the sinogram is missing. And if you recover with classical methods, this is what you get. So you see it looks awful. This is the best we can use with model-based methods, where we have a precise mathematical model, where we don't learn anything. If you use a neural network and forget everything about the physics, this is what you get. And if you combine both, you see you get a much better result. So this is, so I think in that sense, deep neural networks have a tremendous impact. You have to use them in a good way and also combine them what people have done before. Now, certainly all these model-based methods come with a lot of theory. People have worked on it for many years and developed and really understand error bounds, when they work, in which setting they work. Then if you combine them with neural networks, there the theory is not at that stage yet. And so this then also encouraged me to delve into the theory of neural network and to contribute there. So what about the theory of neural networks? Let me show you, or let me say what the key directions are from my perspective. So what is a neural network? Just to recover and bring everyone to the same stage. So a neural network is, from my perspective, a function of this type, where you have here affine linear functions, so ax plus b. So the a are the weights in the neural networks, and the b are the biases. Then we apply an activation function, a nonlinear function component-wise, then another affine linear map, and so on. And so this corresponds to this depiction, where this now mimics these affine linear maps. So this is our neural networks. So very, let's say, complicated functions, highly structured functions. And what do you do with those? Well, also there, I think, let me just recall to then from this derive the directions which are interesting to me. So you have sample values of a highly complex function, which is maybe defined on some lower dimensional object. You then select an architecture. So you select how many layers you have, how many neurons in each layer. Please, yes?
Sorry, it's a minor thing, but your picture doesn't match your formulas, right? Like, your formulas are for fully fit.
Oh, you mean here? Or here? I'm sorry, where?
No, the neural network. It should be fully connected, right?
Here. Well, so it depends. So this is just a depiction. So what I mean here is you just select a neural network, and you need to decide how many layers you take, how many neurons, and you might also pre-select certain entries to be equal to 0 in the matrix. Yeah, so you can take a fully connected network, but you can also take a network which already has a specific structure. So for instance, if we solve these inverse problems, which I talked about before, then you pre-select certain entries to be equal to 0, so you take so-called units for that.
And you don't train them.
So it's just this is just an example image. So you could train. This is just one example of a neural network you take, and then what you do is you learn these entries of these affine linear functions. And so the entries correspond to the weights on these connections and the biases which you have in every neuron. Does this answer your question, or?
It's not.
Okay. Okay, so anyhow, so you select an architecture, however it looks like. It can be fully connected, it can be different. And then what you aim for then, you would like to learn the weights and the biases. And so you do this typically by an optimization procedure where you aim that the network evaluated in your sample points xi is close to the sample values f of xi. And you take a loss function, let's say the square loss or so, to analyze or to measure the distance. Maybe you would also like to have sparse weights or something of that type. So you also regularize this and take the minimum and solve this minimization problem, usually by stochastic gradient descent. And then you hope that in the end, your neural network is close to F. So if you look at this procedure, you see that several questions arise. The first question, and this also relates maybe to your question, is so-called expressivity. So you have a neural network architecture. How powerful is it? Now, if I can choose the weights freely, and I would like to approximate a certain function, is the network actually capable of doing that? Does it have enough approximation or expressivity power to approximate the function classes we aim to learn? So that requires a lot of light harmonic analysis, approximation theory, questions of this type. The second is the learning procedure. So I have a learning algorithm, like the stochastic gradient descent. Does it converge? What are good starting values? Does it converge to something reasonable, local minima, global minima, and so on? So this requires tools, for instance, from optimal control, optimization, and in this direction there are also interesting results. Then the area of generalization. So I train my neural network on my training data, but it should also act in a reasonable way on my test data. So not only should it perform on the training data, so on the xi's from the previous slide, but also on other points. So it should overall, if you go back, approximate the entire function f. And if you look at those areas from a theoretical perspective, maybe the best explored is the area of expressivity. Maybe the least explored is the area of generalization. And so these three areas also have a certain correspondence to, in general, neural networks. Namely, if you view a neural network as a statistical learning problem, then these are exactly the three components which you need to analyze for your error. Because if you look at a statistical learning problem, you have three types of errors. You have the approximation error, because you have the hypothesis class and you would like to approximate in it. You have the error which comes from the algorithm, the optimization error, and you have the error which comes from the fact that you just have sample values. And these you would like to approximate. And so in this talk, I would like to focus on first this generalization aspect and tell you a bit about what we did in this direction. Now, as I said, this is the least explored area. And I would be happy to tell you, a very comprehensive result which solves all problems, which I cannot. But let's see what we can do. So as I said, it's an area where there's not that much known yet. There are very interesting contributions. If you look at this list of contributors, you see, there were older results where people introduced something like BC dimension, Rademacher complexity, and so on. And then there are newer results where people now aim to understand in detail this phenomena, which people call the double descent curve. So the double descent curve is the following. If you have, let's say, a learning problem, or here a neural network, this is the capacity of it, so in the size, and this is the risk. Then you have this phenomenon that if you go down here with the training risk, so as you increase the capacity, but the test risk then after some point, which is called the sweet spot, again increases. And so this picture is to some extent explained by statistical learning theory. But this is not what we observe in neural networks, because there we observe a nice and interesting phenomena that the test risk then goes down again in the over-parameterized regime. So therefore one says, take as many parameters as you can and train your neural network. And so this part is not explored and not understood at all. So as I said, I cannot give you a complete answer why this works. I would like to now look at a very specific situation of neural networks, and for that analyze one aspect of generalization. And the neural networks I want to look at are convolutional neural networks. These are neural networks which not act on signal on the Euclidean domain, but on signals on graph domains. And so there are interesting contributions, how to design and how to set these networks up. They are very important for applications, for instance, for recommender systems, also for fake news detection, so for social media in general, and also in the sciences, for instance, in chemistry. I mean, we have, let's say, the molecular structure is also like a graph. Yes?
I have a question. Why do you say that there's no work on the right part of that center?
Okay, so I should say it's not, there's no work, but I mean, it's not fully understand why it actually goes down.
But so you're not really
Sorry?
with margin theory?
Yeah, so that's right. But I mean, to my extent, I mean, it's not really that you can fully understand it. Sure, there is work in that direction. Absolutely, I agree with you. Okay, so these are applications of graph neural networks. Now, graph neural networks have a specific problem, which doesn't occur if you have data on Euclidean domain. Because for graph neural networks, your training data now consists of graphs. And so the network sees some graphs and trains on those. But it could be that in the test data set, you have graphs, types of graphs which the network hasn't seen before. And so if you would like that this network generalizes, then if you have two graphs which somehow give you the same or mimic the same phenomena, then what should happen is that the network acts similarly on both graphs, although it didn't see one of the graphs. So if you have, let's say, two graphs of this type, they somehow mimic the same phenomena, then if you now take the graph convolutional network, it should have somehow the same repercussion on both graphs. So that seems reasonable. So this is in some sense a necessary condition for the network to be able to generalize. Okay, and so what I would like to show you here is that you can actually rigorously prove transferability if you have a graph convolutional neural network which is based on spectral filtering. So let's take a look at filtering in more detail. So you have basically two different approaches. You have the spatial approach, where you have your graph and you put your filter directly on the graph, and then the convolution is basically moving the filter around on the graph. There's the other approach, the spectral approach, where we use the convolutional theorem. So convolution on the graph in spatial domain corresponds to multiplication in the Fourier domain. And so the spectral approaches now act in some sense in the frequency domain. And there's a common belief that these graph convolutional neural networks with spectral filters do not exhibit transferability. Whereas it's the belief that for spatial approaches, it actually does. Yes?
Sorry, I almost don't know about graph neural networks. Is the input an adjacency matrix and the output a number, or like what's the?
So the input is a graph, and the output could be, for instance, a number. I mean, depending on if you want to classify, for instance, graphs.
How do you input the graph? As the adjacency matrix, or?
For instance, yeah. Yeah, I mean, I will go into a detail a bit in a moment. Also, how filters look like. Okay. Okay. So this is the common belief, and what I would like to show you now, this part is that this is not true, so that indeed spectral graph convolutional neural networks can or do exhibit transferability. So this is exhibit this phenomena which we need for generalization. Okay, so now let's look at spectral filtering. So how does spectral filtering work? So if you think of the Euclidean domain, there you have the Laplacian, and then you look at the frequencies through this, and you can do exactly the same also for graphs. So what you can do is you can define a so-called graph Laplacian, which you define in this way. So you have here the so-called degree matrix. So on the main diagonal for each node, you have how many connections you have. And then you take the adjacency matrix here, and this difference is the so-called graph Laplacian, unnormalized, and then you can also normalize it. So in the Euclidean domain, this is the canonical Laplacian, which we know. This is an operator. It's self-adjoint, so you can define or consider eigenvalues. and eigenvectors. So the eigenvalues correspond to frequencies, and the eigenvectors then to Fourier modes. So in the Euclidean setting, these would be these exponential functions, which you know from the Fourier transform. And in a sense, I mean, the graph Laplacian corresponds or links very closely to the geometry of the graph. So if you have a graph like this dumbbell shape, then you see, if you look at the Fourier modes now, these frequencies, they kind of obey also the geometry of the graph. So you see here the first eigenvectors and then others which then give higher frequencies also in these two dumbbell shapes. Good. So based on this, we want to define the filtering process. And the most canonical you could do that is by acting on a graph in this way. So these are now the filter coefficients. And if you compute this sum, this would be the typical way to define how a filter acts on a graph. Now, so these are the eigenvectors of the graph Laplacian.
Sorry, I'm so confused.
Yeah, okay.
For you, a graph is a collection of edges and vertices?
Yes.
So I think
So maybe we can just. So you have here something of that type.
yeah, this CF, is that a vector?
So the CJ. You mean the CJ? So the CJ are coefficients, like filter coefficients.
The whole object is right. CF, that is a vector?
So this UJ, if we go back, so the UJ is an eigenvector, so it's a function on the graph.
Okay, yeah. So for every vertex, you have like a component of your vectors, and the thing that you output is like a weighted combination of the vertices.
In a sense, yeah. Okay. Okay, so this would be the canonical way to do that. There are certain problems with this because this approach does not exhibit transferability, so we need to modify this slightly and take let's say a very specific graph, a spectral approach. So what is the problem with this? Well, I mean, first of all, you see you need to compute these eigenvectors, which if you have a massive graph, like a friendship graph, it's just not possible. And also for computing this, you need something like the fast Fourier transform, which also doesn't exist for in general for graphs. But you also see another problem. You see, I mean, now what we want to do is if we have our graph and we maybe perturb it a little bit, we want that the filtering process is kind of invariant under that, so that the repercussion of the convolutional neural network is the same on also a slightly perturbed graph. But if I perturb the graph a little bit, then I'll go back, then the graph Laplacian will be also certainly perturbed. And this causes the effect that also the eigenvectors might be perturbed and might be actually very perturbed because these are not even unique. And so you see, I mean, then you can never ensure that if you perturb the graph a little bit, that this gives then the same repercussion. Yeah, so their transferability is not possible. So we need to define spectral filters in a slightly different way. And the way we define it is by what's called functional calculus. So let me walk you through that, and then we come to the transferability part. Okay, so what we do is the following. So now we have the graph Laplacian. Yeah, so think of this now as the graph Laplacian, and we can expand it. This is the normal spectral decomposition. So we have here the eigenvectors, we have here the eigenvalues, and I can decompose it in this way. So this we already saw before. Now, I would like to do the following. I would like to take a function, and this will be later on my filter instead of these filter coefficients. I take a function, and I want to let it act on my operator, on my graph Laplacian. And one can do that in such a way, and it's a general theory, that then from this new operator, so I have my operator, I apply this G, and it gives me a new operator. From this, if I write this operator now, then the eigenvectors remain the same, and only the eigenvalues change, namely in such a way that I apply G now to those.
Sorry.
Yes?
I still have no idea what's going on. T is a matrix. Or
You can think of it as a matrix. You can think of it, yeah.
G is a function from R to C. So why are you thinking G is T? I don't understand.
Oh, sorry. Yeah, that's actually, sorry. This is actually a typo. So the G is in a higher domain. So this is a typo. Sorry. So G acts. So if this is, let's say, an operator on the operators, or it acts on RD or on matrices.
Okay, but then I don't understand the other side. What's the example?
Okay, so maybe we'll make an example for that. Yeah. So if G is a function of this type, like a rational function, then, actually the G, this is correct. So if G is this, like a rational function, then G of this operator, so this is, would be defined in this way. Yeah, so this is a general theory in some sense. So if this G is, for instance, the function which just maps x to x squared. Yeah, so maybe let's make an example. So if G is the function, is this function, yeah? So then G of t would be just t squared. Or if it's, so you can think of t as a matrix, or G of a would be a squared. Yeah, so it's a means, if you have a matrix or in general an operator, to apply a function to it. Yeah? So if my G is just a square, this is a more complicated one if you have a rational function. So then if you apply it to your matrix or to an operator, it does basically the same. It replaces this x now with this object, this matrix, and it gives me t squared. Yeah, so this, I guess, you can just define. And then, you have something more complicated, and G is more complicated than this, or a rational function. There's a theory you need to develop. It's not immediate. It's just, what one needs to keep in mind is if one has such a G, one can apply it to a matrix. And in simple cases, like if you map x to x squared, or if you map lambda to a rational, if it's a rational function, then it gives me an object like this. Or here, in the special case, it gives me t squared.
Okay. So if G of x is square root of x, then send every eigenvector t to the square root of lambda x.
Yeah. Okay, so what is the advantage of all this? This looks very complicated, but what is the advantage now? The advantage is that, you see, what we do now is we take a G. This is now our filter. Instead of these coefficients, we take a function, and we apply it to the graph Laplacian. And then, from the previous slide, we get something like this. And now, comparing this, we see here we had the problem that, first of all, we needed to compute these UJs. And also, if I perturb my graph a little bit, then these UJs can be significantly perturbed. But these keep constant. So therefore, this whole sum might really, be very far off from the original version. Now here, let's assume my G is also a rational function. Then to compute this, one doesn't even need to compute these UJs. Yeah, because, I can just compute this. For this, I don't need the eigenvectors. So I don't need to compute the eigenvectors for it. Also, if I now perturb my graph a little bit, then, again, the graph Laplacian may be a little bit perturbed. The eigenvectors might be perturbed, but one can show that although these might be perturbed, this is then also perturbed. And in a sense, it compensates for the perturbation of those. Yeah? So here, this remains fixed. So if this is perturbed, then, this might be far off, but here, this compensates for it. And so one can show that in some sense this is stable. And also if G is a rational function, one can compute this. Okay, so this is in some sense the approach how to design spectral filters in such a way that you have stability and that you can also compute those. No? Are there? Is this somehow any questions to this right now? Yeah, so the idea is instead of taking filter coefficients here, we now take a filter as a function, G, and we apply it to a graph in this way. Okay. Okay, so what about transferability? Now, I mean, what we need is we have these, let's say, two different graphs which give us or which mimic the same phenomenon. This we need to understand. What does it mean? I have different graphs. They realize the same phenomena. How do I make this precise? And what I do by this is I look at it from a more general viewpoint. So a graph, I have certain nodes, and then I have weights between those nodes. Then, so maybe let's look at it this way. So what we do is we think of graphs as a discretization of something which is continuous and above that. So what is continuous and above this is we can view as a so-called metric space. So metric space, just think of you have points and you have distances between points. So a metric space would be you have, I don't know, you have points and you have a means of measuring the distance between 2 points. And what we do now is we view a graph as a discretization of such a general space in such a way that if I have 2 points in my graph and if I have certain distance there, if I have 2 points in my graph and it has a certain weight, the edge, then this corresponds in some sense to the distance between the points in the metric space. And if this distance shrinks, then the graph weight will increase. So this gives us a means to put everything under a broader picture. And there we can compare. So that's the idea. So now if we have graphs which explain the same phenomena, then what it means is they come actually from the same metric space which lies above them. So here, I mean, just visually, if you have two different graphs, I mean, if you have this, let's say, this continuous object, then you can have certainly different discretizations. But these, we view them as measuring the same phenomena if they come from the same space. Yeah.
Convergence to operator.
Sorry?
You're assuming that the graph of line converges to operator.
Yeah. So convergence, so here it's just two discretizations, but then you can refine the discretization. Yeah. Okay, so this gives us a means to compare. Otherwise, I mean, there would be just different graphs, and we don't have any means to compare those.
Don't correspond to a Laplace-Beltrami operator. What? I mean, that's like most graphs. Like, if they don't correspond to the discretization of Laplace-Beltrami.
Mm-hmm. So sorry. So what is what?
Correspond to the discretization of the Laplacian operator on a domain. What do we like? How do we compare those types of graphs? Those are most
So.
Graphs we encounter. So, I mean, these are what graph neural networks. Social networks are not going to correspond to.
Yeah, but what do we mean with correspond to? I mean, so the way we view it here, and certainly there are also, let's say, conditions on the theorem later on. So the way we view it here is, I mean, we have, let's say, think of maybe a manifold.
Yeah.
Think of it a manifold, and then you can think of discretization of it in some way. And if you have, let's say, two different discretizations, then this, I mean, per se, would already at this stage, without any additional hypothesis, mean it represents the same phenomena.
What does it mean to be transferable if I have two social network graphs?
We will come to that. Yeah. Okay, so let me explain to you now how we can compare via this, let's say, general viewpoint, whether filters have the same repercussion. Okay, so we have these two different graphs. Now, what we do is we take a signal now on these metric spaces where these are discretizations of. So we have the signal now on those. Then we bring it down to those two graphs by sampling. So we have some function on the metric space and we bring it down to both graphs. Then I apply the filters to those. So I take the same filter, and remember the filter is now applied to the graph Laplacian. So here I have a different graph Laplacian than here. So these are my two filters, which come from the same, let's say, filter, but adapted to the two different graphs. And then I bring it back again to the metric space by some interpolation procedure, and then I have a means to compare. And then I'm asking, is this close? So I have my function on the metric space, I bring it down to the graphs, I apply the filters, and then I bring it back, and there I can compare it. Okay, so let's make this precise. So now I have a metric space with the graph Laplacian. This is what I have on top. I have my graphs with the graph Laplacian. Now, functions on the metric space, I need to decide which to take. So canonical are band-limited functions. So because now I have this Laplacian, I can also define what I mean by band-limited functions on the metric space. But just think of this as certain functions which are defined here. And then I have these means to bring it from these functions. These are these Pay-Levinas spaces. So this function on the metric space down to the graph and back. And so what we can show there, and this is joint work with my postdoc, Ron Levy, Alex Bronstein, and two master students from Italy. What we can show is that this error, so this is the first result, we will then compare two different graphs. So what this shows is that if we have a discretization, so if we have now one element of my defined on my metric space, I bring it on the graph, I apply the filter, and I bring it back to the metric space. And if I compare this with if I just basically stay on the metric space and just apply the filter on the metric space and don't bring it down on the graph, then this error can be bounded in this way. And you see, let's say, roughly what it means. So the transferability of the filter you can estimate. And this is the first part, but transferability of the graph Laplacian plus the consistency error. So in detail, what you do here is, again, you have your function, you bring it on the graph, you apply the graph Laplacian, or you first apply the graph Laplacian and then you bring it down. This is the first part. And the second is, if you have your function, you bring it on the graph and you bring it back. Basically, you check how close this procedure, without doing anything else, is to the identity. So this basically compares with, if I apply the filter on the graph, how does this compare if I don't do anything? And now certainly I need to do the second step to check the distance between if I have two different graphs. So this I can apply not only, and maybe this also answers the question which was asked before, if I have here a metric space and a sample graph, I can also, M could be also already a fine graph, and G could be a coarsened graph, or M could be a graph, and G could be a perturbed graph. So there are various different settings where I can apply this to. And so this, so let me walk you through this. So this is now I have two different graphs, and now I really want to compare if I have the same filters on the graph, and I have different graphs which mimic the same phenomena. Is this transferable, and what is the error? So you have two different graphs, two different graph Laplacians. They come from the same metric space. And I have a graph convolutional neural network with ReLU filters. And then what I do, and maybe please take a look here first. So I take now my function on the metric space. I bring it down on both graphs. I propagate it through the neural network. And I bring it back to the same metric space. And then I compare. the result. And so the error which I make, you see how it is bounded. It is bounded. You see the number of layers comes into play here. D, which is a constant depending on the filter, which shows the dimension of these spaces which I use as starting spaces. And this delta comes from these estimates. And now if you recall, these estimates, if I go back 2 slides, these were exactly these 2 components, this component and this component. So transferability of the Laplacian and the consistency error. Yeah, so this shows and gives an estimate if I have the same filter on these 2 different, if I have the same filter, if I have 2 different graphs and I input it in my neural network, what is the difference there? And these 2 graphs, if they come from the same metric space, so if they are discretizations of that, meaning they mimic the same phenomena. Yeah? So again, I have 2 different graphs which mimic the same phenomena, meaning they come from the same metric space. And now I wonder if I let my neural network act on this and I act on this, what is the error which I make? And this is exactly the error which you obtain. Yeah, so in that sense, usually, as the number of layers increases, it gets worse, which actually makes sense because then I pass my graph through many layers and I get a lot of more, let's say, effects on my graph than if I have a very shallow network. Okay. So also concerning transferability, what one should be aware of is that there are various ways or different aspects of transferability. There's the concept-based transferability, which says I have already different graphs in my training data set, which mimic the same phenomena. So the network already learns how to transfer between different graphs. And then I have a new one which mimics the same, so then it might be easier. Then I have the principal transferability, where I just have from one type of graph, and the neural network cannot learn how to transfer. It can only do that by, let's say, some intrinsic property. Yeah, so this is basically, what we also estimated here, the built-in capability of neural networks, of graph neural networks, to transfer to other types of graphs, which mimic the same phenomena. So let's look at some numerical experiments. What we do here is we have, let's say, a picture. We look at different resolutions. And the neural network just sees one resolution in the training data. And so the question is, can it also deal with other resolutions? Yeah, so here you have basically, this is this case where you just have one single graph training set. And so what you see here is, so this compares spectral via spatial approaches. You see if you do that, then the spatial approach degradates much faster than the spectral approach. So the spectral approach has this built-in capability of transferring from graphs to unseen graphs if they mimic or if they realize the same phenomena. And another example is graph perturbations, where now you have a graph and you perturb a little bit, you put that in, and so this compares the filter error versus the Laplacian error, and it basically shows that, you see it's a linear correspondence, so this shows that, the estimates which you get are very close to being sharp. Okay, so this was one part of generalization where we look at graph convolutional networks and we look at a very specific type of generalization, somehow a necessary condition for generalization. If that's not true, and if that doesn't happen, then graph convolutional networks could not generalize. So if you have the same phenomena, then you certainly would like that the neural network acts on the graphs and those graphs in a similar way. As I said, 10 minutes, 15, yeah. So as I said, there's another aspect which I also want to briefly discuss, which is interpretability. Now, interpretability is a very different question. I mean, it basically neglects everything which has been done before, and it just says, no, I have a neural network which is there. I don't know how I got it. I just have it, and I would like to understand how it operates. And why is this important? Well, I mean, I would like to open this black box, and there are various examples. So, for instance, if someone applies for a job, this is rejected, and if this was done by a neural network, then certainly one would like to know why was this job application rejected, what were maybe key important criteria for doing so, maybe, I don't know, the salary, the previous salary of the person, or whatever. Because in a sense, I mean, the one who operates the algorithm needs to tell the applicant why was your job application rejected. And so, in some sense, the holy grail in this area is to derive an explanation which is indistinguishable from a human being, where we are very far off. But in the end, I mean, this is what you might like to have. So if you use neural networks in your algorithms, you would like, in the end, also to give reasonable explanations of why decisions were reached. Also in the healthcare sector, if their decisions are reached concerning treatment of patients. So you need to get that out of the neural network. There is already a lot of work in this area. There are gradient-based approaches, backpropagation approaches, surrogate model-based approaches, game-theoretic approaches, and so on. So what these approaches aim to do is the following. So let's look at MNIST. So you have here a 3, for instance, which you would like to classify, and you would like to understand which pixels are important for the decision. So this is, in a way, the easiest situation you can look at. And what you would like is you would like to have like a heat map indicating for each pixel how important it is. So for a 3, for instance, this opening is important because it distinguishes a 3 from an 8. But this area is actually not that important because, and it plays even against being a 3 because it seems to almost close this gap. And so this is what you would not expect of a 3. So, and so for instance, if you would like to classify this as an 8, then these openings are actually not that good because, I mean, this indicates that it's actually not an 8 but a 3. So these are relevance maps. I mean, these heat maps which you see here, people call relevance maps. They indicate which pixels are how important for the decision. Now, what we ask ourselves is, what is exactly relevance? Can we make this somehow theoretically precise? And so what we do there is we do that by information theory. And this leads then also to the fact that we can formulate this as an optimization problem. So you have a very precise form which gives you a hand on how good your relevance map is. And so this allows you also to theoretically analyze the complexity of this problem and also to fairly compare different relevance maps. Okay, so let's look at the problem which we have. We have a classification function, and this doesn't need to be a neural network. It can be a very general classification function, whatever you can think of. I have a classification function, and I have an input signal. Now, let's assume I have this image. That's my input signal. I would like to determine what are the most relevant components of it. So this I call S. So this is the set of pixels. So it could be maybe this part. Now, so these I want to say these are relevant ones. So this S also ideally should be small. I mean, if everything's relevant, that doesn't make much sense. So somehow also humans, if you look at this picture and you're asked, what is this? You will also only look maybe at this part and say, well, I mean, this is an ape. And so this we would like to be small, and these are my relevant pixels. The complement of this I deem to be not relevant. Yeah, that makes sense? Okay. Good. So how do we set it up? We want to make precise what relevance is. And we want to use rate distortion theory for that. So what is rate distortion theory? So rate distortion theory is the following. You have two persons, usually Alice and Bob. Alice has some message, and Alice sends a message to Bob. How much she sends is the rate, and then how good Bob can recover the message is the distortion. And now we want to put this in this framework. Okay, so Alice has the following things. She has the original image, and she has a neural network, or a classifier. I mean, it doesn't need to be a neural network. It doesn't depend on that. She has a classification function and the image. Bob only has the same classification function. Now, Alice wants to, in some sense, transmit this decision to Bob. What she does is she can only send a couple of pixels to Bob. She wants to send as few pixels to Bob as possible, but Bob should still get almost the same classification. Now, Bob receives this partial image, hopefully the relevant pixels, but he has a problem now because this is not the image size. He cannot put it in his classifier because the classifier only operates on data of that size. So now what he does is he wants to not disturb this, but still blow it up to a complete image. And so what you can then do is you can complement this with random pixels. So now Bob has data of the same size. He can put it in his classifier and he get a response. So now how many pixels Alice sends to Bob, that's the so-called rate. We want that to be small. But we also want to be small the distance between the classification decision of Alice and Bob. And so you see this is a trade-off. I mean, if I send fewer pixels, certainly the distance will become larger. And to set up the notation a bit, so I complement this with noise. So this is my n, so v is some distribution. And so y is on s, on the relevant pixels, it's just x. And on the complement, it's the noise. Okay, so this is copied from the previous slide. So now the error which we make is the distance between the classification decision, which Alice does with the original image and with the classifier, minus what Bob does, since he only has this obfuscated version, and phi. And then what one aims for is we have, let's say, some epsilon. I would like that this error is small, and I'm looking for the minimal number of pixels which Alice can send, and these are my relevant pixels, because she wants to send relevant pixels, but so that the distortion is small. So this gives us now a means of a definition of what relevant pixels are. Okay. So now, I mean, this we would like to compute, but we actually have a problem now, because if we do this just out of the box, this is an NP-hard problem. So let me just tell you what you can show, and then I would like to show you what we can do to fix this and show you some numerical results. So the way we set this up to show that this is NP-hard is we just look at the binary setting. That's a special case of what we had before. So now I have a classifier just operating on 0, 1 to D. My signals are also just binary values, and my noise distribution also just acts on 0, 1, D. And a Boolean function one can also regard as a special case of ReLU neural networks. So neural networks with a special activation function. So in that sense, it's not a restriction. And so if this is already NP-hard, then the general case will be anyhow NP-hard. And what we can show is that, and this is joint work with 2 of my PhD students and 1 master student in my group, determining whether the number of pixels I can send for a certain distortion is less or equal than k, this is NP-PP complete. And already approximating it within some factor is already NP-hard. Yeah, so basically it's out of the question to compute this precisely, because it's also a binary problem. I mean, it's not maybe that astonishing that that's NP-hard. So what is this NP-PP complete? It's a special complexity class. It comes from artificial intelligence, where basically you have some agent with some precise deterministic plan. You have some random behavior which affects it, and you would like to compute the success probability of that. Now, So what do? You have something which is very hard, which is NP hard, so you just relax. How can you relax it so that you can actually compute it? You see, everything is discrete here, and that's the problem. So you have your relevance set, which is a subset now of your complete image. You have this obfuscation, the distortion, and then the rate. And we make everything now continuous. We don't say this pixel is relevant or not. We say it has a relevance value between 0 or 1. So then, you can define the obfuscation in a similar way by pointwise multiplication. The distortion you can also define similarly just by now using these S. And instead of just counting the number of points in your relevance set, you take the little L1 norm. So if you're familiar with compressed sensing, that's the same relaxation which is done there. Just counting the number of pixels or non-zero elements instead of looking at the little L1 norm. And so this now enables us to really precisely formulate this minimization problem. So now what we do is we minimize the distortion and the L1 norm with lambda balancing between both, subject to S being in 0 or 1 to D, so every pixel now gets an importance value between 0 or 1. So how do you compute this? Well, first of all, you can actually compute what the distortion is. You just plug things in. Then you get here the expected value of phi of y and the covariance of phi of y. What you can compute, though, is the expected value of y and the covariance of y, but not of phi of y. So these you can explicitly compute. Now you need to get from the expected value and covariance of y to the same for phi of y. And so there are various ways to do that. One is just to sample the mean covariance if you have just a general classification function, or you use, if you have a neural network, you use the structure of the neural network, you propagate the expected value and the covariance through the neural network. So how do you do that? Well, let's assume you have a Gaussian distribution. You want to propagate it through your neural network. You first propagate it through the F1 linear function, which remains a Gaussian distribution. But then you have a problem because then you propagate it through the so-called ReLU, so to the nonlinear activation function. This distorts it, and it doesn't remain a Gaussian anymore. And so what one can do is one can do moment matching and then take the closest distribution, and then keep going. Okay, so let's finish with some numerical experiments. This is a classical database for handwritten digits. We take a fixed neural network, which has a certain test accuracy, so it's an almost perfect neural network, and we want to understand it. And here are some experiments. So this is my input image. And these are different explanations on why the neural network classifies this as a 6. So these are all different methods. So deep Taylor, backpropagation, Lime, and so on, and these are ours. What you see here is that this area in the 6 is also deemed important. Why? Well, because, as I said before, if you close this, then it's not a 6 anymore. So this area, this opening, this gap here is indeed important. So and also this part is important, this lower part, because it also indicates that somehow it contributes to the fact that that's a 6. But then you can say, looking at pictures is nice, but it's not fair. You would like to have a comparison measure between all those different methods. And so this is one way to look at it. So what you see here is how many pixels you actually take to be important versus which error this causes if you just take those pixels. And so you see here the comparison of all different algorithms. What you observe is that in the low rate regime, so if you take very few pixels, our algorithm performs the best. So these are different diagonal and low rank. So these are different versions of this moment matching. then here, after some point, I mean, it coincides with other methods. A big larger data set is STR10, so these are natural images. Again, we take a fixed neural network with a certain test accuracy, and you see here one example, again, an image with different explanations. What you see here with our explanation is that basically, I mean, the head is important, and somehow the outline of the head is deemed important. And again, now looking at the comparison, you see in the low regime, ours outperforms the others. So if we really aim for, let's say, sparse explanations, very few relevant pixels, then this is outperforms the other methods in this respect. And as I said, we have a theoretical understanding of this approach. So from my perspective, deep learning, and that's how I came to it, is extremely, or performs extremely well for also not only, let's say, in public life, but also for mathematical methods, like for inverse problems, partial differential equations, and so on. The theoretical foundation, though there are various open questions in these, I think, 4 regimes: expressivity, learning, generalization, interpretability. I discussed with you 2 of those. So for generalization, I showed you one aspect of generalization for graph convolutional neural networks, which is necessary for their generalization ability. And then we moved to the area of interpretability, where I showed you an approach which, to my mind, or to our minds, has now a bit more theoretical foundation, so that you really know what is relevance and how you can define relevance maps. And with this, I'd like to conclude, and thanks for your attention.